So welcome to lecture number 45, the Statistical Thermodynamics course. Now, as you can see that we wrote that from the two-level energy system, we wrote that this was the expression when you take into account the spontaneous emission, the stimulated emission, and the absorption. And we also have written the Planck's formula, okay, and because this is the radiation density. So it looks like that if both of these two expressions, if they are valid, then it can be valid in only one way. That means your B10 should be equal to B1 to 0. That means and A1 to 0 and by H. B0. Okay, so this essentially proves that the rate constants, okay, for absorption and stimulated emission, okay, which are basically two very different physical processes, are identical. Okay, and it also shows one other thing, that the spontaneous emission coefficient, which is basically this guy, okay, spontaneous emission coefficient can be determined from the absorption coefficient. Okay. But you note this particular factor. This is very important. This is the relation between, your spontaneous emission and your absorption. So they are linked by this particular factor, which is cube. Okay. So this plays a very role between the two, very role in the competition between the induced and the spontaneous emission processes. So this is important, and we can see that how this can be determined from the absorption coefficient also. Okay, so that's all very good. Now let us look at the absorption and emission of radiation. What are those? Absorption and emission of radiation. Okay, so the interaction of electromagnetic radiation with matter can be described by a simple semi-classical model that we already know. So this is obtained by the time-independent solution of the Schrodinger's wave equation, correct? Okay. In the semi-classical treatment, the energy levels of the molecules are obtained by the solution. So let's write it in the semi-classical system. The energy levels, okay, of molecules are obtained by the time independent solution of Schrodinger wave equation. Okay, so that means essentially this. So while the electromagnetic radiation is treated in a classical fashion, classically. So if we consider a two-level system, okay, so let's look at a simple two-level system once again. And E1 minus E0. So, okay. So this is a two-level system which is characterized by the two wave functions, upper and the lower wave functions. The electromagnetic radiation that fulfills the Bohr condition is this. It is precisely tuned to the two energy levels. It's also given as, okay, this is applied to the system to induce a transition from the lower state to the upper state. So the molecules consist of nuclei and electrons at positions Ri, possessing charges Qi. So you all know about this. So if we have a Cartesian coordinate system, so the system will have, we can express that the system will have a net dipole moment in the, if we write it in a Cartesian coordinate system to begin with. It's X summation Xi Qi. Then there is mu y, is written as yi Qi. So this is the dipole moment. The dipole moment, which is so the system can have a net dipole moment because it has got nuclei and electrons at different positions carrying charges Qi. So Qi are the charges, and Ri is basically nothing but the position of the nuclei and the position of the electrons. So these electrons are basically what are distributed in this particular way. So it's like this. Okay. Y, Z, X, something like that. So there may be Q3, Q1, there may be something like Q2 somewhere. Okay. So these are the kind of position vectors, R1, R3. This is definitely your R2. Okay. So they are located at different things. And then of course there's a mu z also, which is summation of Zi Qi. Okay, so this is also given. Okay, where xy, xi, yi, zi are the coordinates of particle I relative to the center of mass of the molecule. Right, center of mass of the molecule, and these are the positions of the particles. So the interaction of radiation with material system is taken into account. We already know about this by addition of a time-dependent perturbation, right? So this is, we already know. We have done it before. So that is what we are going to do. So minus mu dot Et, where E is an electromagnetic field, basically. So dot cos K dot R minus omega T. Okay, so if the oscillating electric field is in the Z direction, okay, and the system is at the origin, the oscillating, say if the oscillating electric field is in Z direction, which means that your E naught is equal to 0, 0, 0, Z, like this, and the system is at the origin, and system is at origin R equal to 0. Okay, and the wavelength is basically greater than the dimensions of the system to avoid having different electric field strengths at different parts of the molecule. So the wavelength is greater than the dimensions of the system, so to say. So H at prime is equal to minus mu Z E0Z cos omega T, which in other words is like mu E cos omega T. So the transition probability is therefore obtained by solving the time-dependent Schrodinger's wave equation. So the transition probability is obtained by solving the time dependent Schrodinger equation. Which essentially translates to I h prime psi by d equal to h hat plus h hat prime d psi. So in the absence of this part, okay, the absence of the prime, the two time dependent solutions will be the two time dependent solutions okay, in the absence of bar is given as psi 0 t is equal to psi 0 e minus I e naught e by h bar, okay, which is equal to I naught e I omega naught t. And when there is psi 1 t equal to psi 1 e1 t divided by h bar, which is equal to psi 1 e minus I omega 1 t, where your omega I is basically ei by h bar. Okay, so this is the time dependent solution, okay, of the time dependent wave function, whereas the other one was a time independent. We can write it with the time independent wave function. So the wave function of a perturbed two-level system, the wave function of a perturbed two-level system, okay, is given by the linear combination of complete set of functions psi naught t and psi 1. Okay, great. So I t is therefore given as a naught. So this is a linear combination. So, and this is basically the time independent part. So e minus I e naught t by h bar plus this a1t given as, again, this is the time independent part, minus I e1 t by h bar. Okay, so in short it can be written as a naught, just dropping the t now, psi naught e minus I omega naught t plus a1 psi 1 e minus I omega 1 into. Okay, so this is the complete wave function. Okay, so these are the time dependent coefficients, a naught and a1. These are called the time dependent coefficients. Okay, so substitution of this particular solution into the time dependent Schrodinger's wave equation. So if you substitute this now, 2I h bar, right? So this is the complete time dependent solution. Okay, if you substitute this solution into that, okay, this leads to the equation like h bar a naught. This is once again the time independent portion. Remember, that's why I'm writing it in italics. A1 bar. Dot means it's a differential with respect to time. Equal to h of a naught I1 minus I omega naught into A1 psi 1 minus I omega 1. Okay, so A naught dot is equal to dA naught by dt. A1 dot is equal to dA1 by dt. Okay, so that is the whole set that we have written. Okay? And so now what we are going to do, multiplication by followed by integration over all space. So let us do multiplication by, once again, this is, I'm writing it in italics, the conjugate, or this is also the conjugate, B, followed by integration over all space, then gives basically yields two coupled differential equations. Okay, so what are those differential equations? A naught dot equal to A naught I naught A1 I naught psi 1 I omega 1 0 into t. Okay, so we will see what those bracketed terms actually means. Let me write down this first, and then of course h bar A1 dot is equal to A naught I1 h bar E I omega 1 0 to t plus A1 psi 1 h at pi. Okay, so these are the two coupled differential solutions. Now, obviously, we're going to ask what those bracketed terms actually mean. So this is the Dirac notation, the Dirac bracket notation, which tells you that this is F1, A hat, this is the operator, and F3. This is what we are trying to say. This is basically integral. F1, this is the conjugate, A, F3, D tau, where tau is basically across the entire space. So no approximation has been made other than that there are two states, psi 1 and psi naught. Okay, so the equations, these two equations that we see over here, okay, they completely have come out. Okay, they have completely come out, are equivalent to the original Schrodinger's equation, except now that we have taken a time perturbed solution and a time non-perturbed solution, right? Now, if h at prime is taken as minus mu e cos omega t, okay, in the electric dipole approximation, okay, Then the time-dependent perturbations, H prime has odd parity, that it is an odd function of the spatial coordinates. In other words, H hat prime is an odd function, okay, since mu is equal to minus Ez. So the products Chi1, the mod of Chi1 square or Chi0 square are even functions. So the integrants are basically odd functions, are also odd functions. Okay. So as we know that all atomic and molecular states that have definite parities, even or odd, with respect to the inversion of the space fixed coordinate system, okay, one can write okay, is equal to 0. So therefore, using this, the equations can be reduced to I h bar a naught dot minus a1 m01 e I omega 1 0 t cos omega t, and then of course I h prime a1 dot is equal to minus a naught m01 e exponential I omega 1 naught t cos omega t, where the integral m01, as we know already, is the same as the other one. It's like mu naught is called the transition dipole moment. This we already have learned. Transition dipole. Okay, and it's the most critical factor in, we already know, in determining the selection rules and everything. It is a vector quantity, okay, and it is m10 is a vector quantity. So it is convenient to define omega r as m10 into e by h bar. Okay, this is also known as the Rabi frequency, after Rabi. We also know that cos omega t is equal to ei omega t plus ei minus exponential form. So therefore, the two equations for the rate constants of the a naught dot and a1 dot, okay, is then written as a naught dot is I a1 omega r e minus I omega 1 0 minus omega into t plus e exponential, it is omega 1 0 plus omega to t, okay, and this is divided by 2. Similarly, a1 dot and as I a naught omega r e I omega 1 0 minus omega to t plus e I omega 1 0 plus omega to t. Okay, so you close the bracket and then you divide it by 2. Okay, so the physical meaning of the Rabi frequency would be clear. So these are the two, A1 and A2, or dA1 by dt and dA0 by dt. So at this stage, only approximation that we can make is omega 1 0 is almost the same as omega, since the system with Bohr frequency omega 1 0 is nearly or is resonant or nearly resonant with the optical angular frequency of 2 pi. So basically what we are trying to say is E1 minus E0 by H bar, which is equal to omega 1 naught, okay, is resonant is resonant or nearly resonant okay, with the optical angular frequency. Omega equal to 2 pi mu. Okay. So the terms, therefore, the terms which is represented as EI omega 1 0 minus omega into t, or E minus I omega 1 0 minus omega into t, they represent slowly varying functions of time, okay, compared to the rapidly oscillating non-resonant terms. Okay, so this represents the slowly varying functions of time, okay, when compared okay, to rapidly oscillating non-resonant terms. EI omega 1 0 plus omega t, and E minus I omega 1 0 plus omega into t. Okay. So we will see in the next lecture that how this approximation and where does it lead to. Okay. So we will cover this in the next class. Thank you.